Okay, it's 40 after. Let's go ahead and get started. Today, I'm going to finish up on rotary motion. I'm going to actually calculate some things. So last time I introduced some concepts. There's a few more I want to introduce about rotational analogs and stuff we learned about linear, rotational analogs and things you've already learned about. And it's all chapter 10 stuff. We're going to skip chapter 11. Chapter 11 is all about angular momentum, which is a very interesting topic, but it gets into using torque as a vector and then angular momentum as a vector. It's interesting. Go ahead and read it if you want, but I won't test you on things from this section, from this chapter. There may be a homework problem or two on angular momentum, on sort of very simplified versions of it, but not the full, not all the machinery that's introduced in the chapter. So we'll skip that chapter, and then next week we'll go on to chapter 12, which is about statics. It's about calculating what the forces are on a beam, on a hinged beam, on a boat or a building or something you build. Architects have to worry about this kind of stuff, structural, mechanical engineers. And it'll turn out that we'll have to use all the machinery we're learning about today with about rotary motion to solve this problem. It's kind of surprising. So we'll do that. Okay, so today I'm going to start off, though, by finishing off that list of concepts we had, and then give you a little more information about torque, and then solve some problems. All right, so here's our list, right? We've got position over here, and over here we have an angle, right, for rotary motion. What I'm making right now is that same chart I started last time. I have linear things over here, right, linear, and over here I've got angular. And what do we have? We have velocity, right? I'll do the x component of velocity, and over here we've got omega. Over here I've got acceleration, and over here I've got alpha, right? And remember, the way to relate these things, you have a circle, a wheel, right, that's rolling along without slipping. You say, how far does the center of mass move? What's that? How far is it translated as it rotates through some angle theta, say? Well, that moved this far along. If that distance is x, I'd say, oh yeah, if this radius is r, which way is it? Is x equal to r times theta, or is r equal to x times theta? What are the units of x? Meters. Units of r is meters. So it better be that r and x are on opposite sides of the equation, right? Otherwise, you'll have meter squared equals nothing, right? And remember, you always think of theta in terms of radians to make these things work out, even though you don't include the radians when you work out the units on both sides. Same thing for alpha and a, right? The x component of the acceleration of the wheel, right, is going to be equal to r, radius of the wheel, times alpha. Meters per second squared, meters over second squared. Yeah, that was right? Yeah? All right, great. So that's just our kinematic stuff. Then we figured out, oh yes, the analog of mass turned out to be moments of inertia, right, which we did an integral for this, but it can be a sum or an integral, but it's in some form it's a summation of all the masses in the problem, right, times how far away they are squared from the axis of rotation. I'm making a little perpendicular sign down here. It's the perpendicular distance. That r is a perpendicular distance from the axis of rotation to this little piece of mass, and you sum them all up, right? That was our mass, moment of inertia. What else did we do? We did torque. Yes, the analog of force is torque. Our definition for torque was it's the right word. It is the radial arm. Well, that radial arm has a specific meaning. I'll define that in a few minutes. But this is actually just the length of the vector that goes from the pivot point, where we define that to be, to the place where the force in question is acting on the object, times the strength of the force, times the sine of the angle between the force and this vector r. And let's draw a picture of this, and I'm going to write it out 3 different ways. Just make sure everyone's thinking about this. There's actually several ways to think about it. The first is, okay, so let's say we've got a situation where maybe I've got a wrench, and I'm trying to torque, trying to exert a lot of torque on some screw, or bolt. I'm trying to turn that bolt, right? What does that look like? Well, here's my bolt. Let's do it this way. Here's my bolt. Here's my wrench. All right, my wrench. And I'm going to pull on this wrench. Now, you guys know what to do. If I want to actually, it's righty-tighty, loosey-goosey, right? Or wait, no, lefty-loosey, that's it. So if I want to put this bolt down that way, right? It's not loosey-goosey, I'm sorry. That's what I get for not studying. So if I grab this thing and pull down, right, then I'm going, that's going to be righty-tighty, makes a right sense. I tend to define this to be my positive direction for rotations. It doesn't matter which way you define it, just stick with your definition. I'll just keep it that way. So we're a clockwise rotation. I'll go ahead and call that positive. So I'm exerting a positive torque on this guy if I pull down right here. Right, so I'm pulling down. So what does the force look like? Well, let's say I pull a force straight down. Here's my force vector, right? Straight down. That results in a non-zero torque. What do I mean by this r right here in the equation of torque? Torque is r times alpha times sine beta. What I mean is a vector that goes from the pivot point, and let's make this our pivot point, right, where the bolt is, the center of the bolt. And we'll make this r vector that goes from that to the place where the force is acting. So my hand is on the end of the handle, and that's why wrenches have handles, right? If they have them, give you more torque, so that for a given force, you can get a bigger r, you get a bigger torque. The bigger your wrench is, the more torque you can exert. Like it doesn't matter how strong or weak I am. If I get a long enough handle on my wrench, I can exert an arbitrarily large amount of torque, right? That's why we have tools, right? Not the fact that this is hard, so yeah, it's hard to really hold on to the bolt. But this fact it's got a handle. If wrenches just had this part right here, it'd be useless. But man, I try to turn that thing, that wouldn't be very good. You need a handle. You need a bigger r that way. So here's the length of r from there to there. There's my force vector. They're at right angles to one another. So I'm being smart. I'm going straight down on the handle to maximize the torque I'm exerting. So what angle is beta? If I take these two vectors and draw them over here again, here's my r vector. Here's my force vector, and let's put them so that they have the tails at the same point. The beta I'm talking about is this angle, the angle between the two. So sine of 90 degrees is equal to 1. That's as big as sine ever gets. That's why, if they're at a right angle, I get the maximal torque for the fixed length for r and f. Okay, great. I'll rewrite my formula. Torque is r times f times sine of beta. Now let's think about other forces I might exert on this wrench. Suppose I exert the forces in the same location on the wrench, but at different angles and different magnitudes. In particular, suppose I exerted this force. Let's call this force 1. So 1, 1, 1. Suppose I have another force I exert like this. So that's a force vector I'll label force 2. It's a bigger force, more newtons, right? I'm pulling harder, but I'm pulling in a direction that's not as well aligned with the optimal direction to pull to maximize my torque. I'm pulling at an angle, right? Now if I ask what's my angle beta, well, if I were to draw a second picture for that, I'd say, oh, here's that force I just drew. So there's beta. Maybe I'll call it beta 2, so I don't get confused about which beta I'm talking about. It's a different beta. And if I ask what is sine of beta, and if I knew this was, whatever it is, 120 degrees or I don't know what it is, some angle, I plug it in my formula. Well, just pictorially, before I do any calculation, I can look at this and know that the torque exerted by F2 is equal in magnitude and in sine to the torque exerted by F1. And the reason I know that is that the orthogonal component of these two force vectors, orthogonal to the r vector, right, is the same. In other words, one way to think about torque is to say, oh, torque is, let's see, it is the full length of the r vector times the orthogonal component of the force vector. And by that I mean this. If I take my diagram here and say, what's the orthogonal component? I say, oh yeah, it's just, so I got this vector right here, my force vector. This is my radius vector. If I take this force vector and ask, what is the component of that that's orthogonal to r? It's just this height here, right? That's what this is. That's f sine beta. Now, some of you might be, by the way, my beta's over here. Well, it's true. It turns out that if I take this angle inside here, right, this angle is what is it, 180 degrees minus beta, pi minus beta. Well, sine of pi minus beta is the same thing as sine of beta, right? So if this is pi over here and this is 0, sine, this is sine of beta, right? Sine of pi minus beta is the same thing as sine of beta. Bottom line is that this thing right here is just sine of beta times the full length f. So you can think of it as the orthogonal component of f, orthogonal to r. Right? You can also think of it this way. You can think of torque as the full brunt of the force vector, right? Full length of the force vector times the orthogonal component of the radius. What does that look like? Well, let's take this example. Well, let's take an example like this. We'll have another force this way, like that, F3. All right, so let's draw that picture. All right, so here's my R. Let's move F3 so it sails over here. Okay, it goes down like that. Now we got a nice acute beta. That's easier to think about maybe. Here's my F. Okay, and so now I say, what's the torque in this case? Well, as I said, one way to do it is to find the orthogonal component of F, which is this. Another way is to find the orthogonal component of R. So I can break R up into two components. I can find its projection along F and the orthogonal part. Right, so, all right, so make a little right angle over there. Okay, so this right here, what's that length? That is R times sine of beta. Sorry, my pictures are sort of blending together here. I meant these to be separate drawings here. These aren't the same thing. Oh, yeah, it's carved out a little space here. Right. So this length here is R sine of beta by alternating interior angles. Anyway, geometry. The point is that all these formulas, they're all the same thing. They're all R times F times sine beta, but you can get them three different ways. And depending on what you're given in the problem description, like if you have a picture, if you have a diagram like this in your problem description, we're all three, like there's three forces acting on this wrench, for example. And you know they all have this, the points of the force vectors are all at the same height here. And the R vector is horizontal vector. You know that all three of these forces are exerting, each of them is exerting the same torque. So if I know the torque that this guy's exerting, it's just multiply by 3, and then the total torque on the wrench, the net torque, would be this guy's torque plus this guy's torque plus this guy's torque. It's just 3 times the torque he's exerting. Because they all have the same orthogonal component. The force is the same orthogonal component in each case to R. Right? Longer force vector, but not optimally lined up, gives you the same torque as having an optimally lined smaller force. And same thing in this case where I'm asking for the orthogonal component of the radius vector, orthogonal to, the component of the radius vector that's orthogonal to the force vector. There's a name for this. This thing is the radial arm. I don't think there is a name for this thing, the radial force or something, or that, I don't know what you call it, the force arm or something. They don't give it a name. But this thing is called the radial arm. It's the effective length R. It's how far, like for this, so in this case right here, let's look at this force over here, F3, acting on this wrench. It says how far, what is the actual distance that's orthogonal to this guy. So if I go up like this, say, oh, it's this distance. So this is the radial arm right here for this force. This is the radial arm for this force. This would be the radial arm for this force. See that? So the longest radial arm for a given force, if you want to change the angle of the force to maximize your radial arm, right? What you do is you make the force orthogonal, perpendicular to the radial vector that goes from the pivot point to where the force acts. And if the radial arm is 0, in other words, if you pull this way with the wrench, you're not going to tighten this bolt down, right? Or if you push on it, not going to do anything, right? That's because you have a 0 radial arm. You're not getting any benefit from the fact that you got a big handle on your wrench, right? So there's a couple different ways to think about it. You can think about the orthogonal component of the force times the full length of the radius, and vice versa with radius. But however you want to think about it, when it's there, the formula you get is F times R times sine beta. But that's a couple ways to think about it. And it's nice to have them all in mind because sometimes, based on what you're given in the problem description, one might be really fast to calculate. Won't require you to do any sine of anything. You'll just say, oh, it's that length. I can read it off the diagram. So it's good to have all this in mind. Okay, so that was torque. And what do we do with torque? Who cares? Like, why do we define a torque? We define a torque because there's a nice analog to Newton's second law, right? So we know Newton's second law says the net force, we'll just do the x component of Newton's second law. The net force acting on something is ma. And so Newton's second law now for rotary motion problems, right, for alpha, what is that? It says that the net torque, I think I wrote this down last time, but I didn't use it, I don't think, is I, that's the analog of m, is I, right, moment of inertia, times alpha, our angular acceleration. We're going to use that in a few minutes to solve. We're going to figure out what's going on with this wheel rolling down the ramp, all right? What else do we have? Let me use a couple more concepts real quick, and then we'll start using these to solve problems. This last one is, that I want to mention for sure, is kinetic energy. So kinetic energy total of a system. And we saw this a couple lectures ago, right? You were talking about how you can have the kinetic energy of the center of mass, and then there's potentially an extra part, right? There's an extra kinetic energy if things are moving with respect to the center of mass. Well, if you have a wheel that's rolling, right, or like the chalk is flying through the air and it's spinning, right? That's a case where if you said all the mass was concentrated at the center of the chalk, you say, okay, it's following some parabolic trajectory, and every moment in time, that's the velocity, you calculate 1/2 mv squared of the center of mass. Well, that's some of the kinetic energy, that counts for some of it. But if I move along with the chalk, there's still lots of motion going on. There's still kinetic energy in my reference frame, right, if I'm moving along with the chalk, with the center of mass of the chalk. So to capture that, we need to have two pieces. We need the kinetic, so first of all, we got 1/2 mv squared, where v of the center of mass, right? That's all the mass, that's the total mass of the system, right? Of my chalk in this case. So 1/2 mv squared, plus I need an angular part. And that looks like this. That's 1/2, well, the analog for m is I. What's the analog of v? Is it alpha? It's omega. That's right. So this isn't alpha squared, it's omega squared. 1/2 I omega squared. So this is a special case of the general case I was talking about before when you've got some motion relative to the center of mass of your system. Like suppose you have two pieces of chalk flying through the air and they're individually doing their own thing. In that case, it isn't a single rigid rotating object. This applies when you just have a single rigid rotating object, right? So I got one piece of chalk. It's spinning and it's flying through the air. I write down its center of mass velocity, I calculate this, and then this is all I have to worry about for that extra correction. In a special case of a single rotating object, it's rigid object, right? Because obviously if it weren't rigid, like my body's not, I'm flimsy, right? If I were flying through the air and I were moving my arms different ways, then it wouldn't work just to know what omega even be. It wouldn't be well defined, right? So in order to say what omega is, you need a rigid object that's rotating, has a well-defined orientation, and you can say, oh yeah, how quickly is it rotating with time? Okay, you get your omega, you square it, multiply by your moment of inertia. If you have a point-like object, it has no spatial extent, well then what's I going to be? What's the moment of inertia for an object where all the mass is concentrated at a single point? What's the answer half the time when I ask out loud? 0. Yeah, right. Answer analysis, right? Anyway, no, I'm just joking. So, well, it's true, but that's not. I'm hoping you understand the idea too. The idea is that I, remember, is the sum of all the parts of mass of the system times their perpendicular distance from the axis of rotation. So if you have an object that's all concentrated at one point, everything's at 0 distance away from the center of mass. So when you calculate the moment of inertia, I didn't say which moment of inertia I meant. I calculate the moment of inertia using a pivot point at the center of mass. Right? Using the center of mass as the pivot point, then it's going to be 0 all at one point. But in general, extended objects like this chalk are going to have a non-zero moment of inertia, even about the center of mass, and this will be a non-zero term, right? In fact, if I have a wheel rolling down a ramp, right, then I'm going to have exactly a situation where I have to worry. We still on? Yeah. I'm going to try and use conservation of energy, which I can use for rotary motion problems. I have to include both these terms. That's all. Make sure I include them both. Okay, great. So let's go ahead. Should I give you one more thing? I'm going to give you one more thing, and then I'm going to solve some problem. The one more thing is a simple case for angular momentum. So we're not going to, as I mentioned at the beginning of the lecture, we're not going to treat angular momentum in its full generality in this class. But for simple cases, we can think about it. And we'll do some fun demos at the end with angular momentum. But the basic idea is that the angular momentum of an object that is a symmetrical object that's spinning about its axis of symmetry, like a really simple case, is I omega. So I need to do this the way I did up there, where I'm separating these into linear and angular analogs. So instead of writing it on this side, let's write it over here. So what's our regular momentum definition? Regular momentum is x component of momentum is, what is it? M times v sub x, right? That's momentum. Well, angular momentum is going to be, they use L for that, and it's and we're Bayesian physicists, and it's equal to what? It's equal to I times omega. So I just stuck in the analogs from over here, right? I for M and omega for V, and this is correct, but it's correct only under special circumstances. Like in this case, I've got an object. It's this chalkboard perfect. Let's say it's flat on top, flat on bottom. It has cylindrical symmetry. It's rotating about an axis that goes right through its axis of symmetry. In that case, I could represent its angular momentum as I times omega, where I is the moment of inertia about this axis, right? Spinning like that. But if I have it spinning another way, or if it's not a symmetrical object, if I take some non-symmetrical object and spin it or whatever, or spin it not about its axis of symmetry, then it's more complicated. So it's good to know that there is an analogous expression, but if you really want to have the full laws of physics working and be able to handle any rigid object rotating in any old way, it gets complicated. In particular, if you have torque acting on something, if you exert a torque on something, right, and the torque doesn't result in just spinning it faster or spinning it slower, it results in changing the direction of the axis of rotation, things get really complicated. And it's a lot of fun to solve. There's a lot of interesting problems there, but they're beyond the scope of this class. But just full disclosure, I just want to tell you that there's stuff out there I'm not telling you. So, and that's a little bit of what they cover in that chapter was 15 chapter left. Okay, great. There's already enough for us to worry about on top board. So let's apply these ideas to the problem of figuring out. Well, first of all, if I have a wheel rolling down a ramp, we did this before, I'm going to remind you. If you have wheels with different moments of inertia, same mass, they weigh the same, they have different moments of inertia, you know what's going to happen. I'm going to roll these wheels down the ramp, and they don't get down at the same time, right? One's much faster than the other. So there's a couple questions. The first question is this an example of constant acceleration? Yes. And it's true. It is. You're absolutely right about that. But why is that true? Can we calculate it and prove to ourselves that that's true? We've already proven that in class, we've done it, you've done it in your homework and stuff. If you have a block of ice that's lying down an incline with no friction, that's a constant acceleration situation, even though the acceleration is less than the full 10 meters per second squared you get if you just drop it, in the air, right? Same thing for friction. If there's kinetic friction, right? Kinetic friction exerts the same force independent of how fast the object is sliding. And that means that the resulting acceleration of the object, even if there's some friction in there, is constant. It's even less than the amount it would have been if there were no friction, but nonetheless, it's constant acceleration. So now we've got another situation where there's a wheel rolling down the hill. So in this case, is there friction in this problem? Is there friction right now? Well, a couple people say yes. Who thinks there is friction in this problem? Yeah, quite a few of you. Who think there is no friction in this problem? A couple people, but most of you aren't voting on this. So who's really not sure? Doesn't know what to think about friction in the context of a rolling wheel. Okay, still nobody, a lot of you want to vote. So here we go. So yes, there is friction, and the way you know that, suppose there were no friction. Suppose there were a frictionless object, or these surfaces exert no frictional force on one another. What would happen? Would it roll? No, it'd just slide down like that. It's hard to imagine that, but in fact, if we had a big steel ball up here and a really slick surface, like ice or something, and it has a big moment of inertia, right? And we design things just right, we could probably set it up so the thing would just slide like this. Maybe from the bottom and start to roll a little bit, but there'd be essentially a frictionless surface. So frictionless, yeah, things would just slide with no rolling. Rolling without slipping. Well, another thing too is if I had it rolling along the ground like this, along the table like this, at a constant rate, a constant velocity, center mass has got a constant velocity, right? In this case, if I started it rolling, even if there were no friction, it would be rolling without slipping, even without friction, because once it's got a certain angular momentum, it would just maintain that, right? But in general, if a wheel starts off, I mean, it's always going to be the case, right? Unless stated otherwise. If you got a wheel rolling without slipping, especially in an incline where it's speeding up over time, there has to be friction for this to be true. What's making the wheel not slip is friction, because otherwise it would start off with some angular velocity, some omega, and it would keep doing that omega even after it's rolled quite a way down the hill. But it's going really fast down here. It would be slipping then, right? It wouldn't be spinning fast enough to keep up with how quick the road's going by. Those of you who play billiards, right, play pool, there's a lot of tricks, or not just tricks, but there's a lot of standard shots where you control where the cue ball's going to go and play English on things that involve the ball sliding with respect to the ground. So the cue ball's moving and it's spinning backwards as it moves forward, stuff like that. But if you're rolling without slipping, you know that, and once again, I think you know this, but is this kinetic or static friction if it's rolling without slipping? Static friction. Because the bottom of the wheel is not moving with respect to the ramp. That's very important. Okay, great. So now we thought this through. Let's go ahead and set the problem up. And what's our question? The question is it a constant acceleration situation or not? And what is the acceleration? So I'm being asked, what's the acceleration, right? We'll say x component of the acceleration. And what do I mean by x? Well, let's draw my diagram. Here's my picture, right? I got my ramp, right? Going down like this. I got some angle theta. Maybe I'll call it something else than theta just because now we're using theta to indicate the orientation of the wheel, right? So maybe I'll call it, and I used beta already. I'll call it gamma. I don't know. Gamma. My angle. Doesn't matter. Just the name for the angle. So I got some angle. I got my right angle. I got my wheel up here. Okay, here's my wheel. What am I given? Well, it's no slip, right? It's rolling without slipping. I'm given the radius of the wheel r. Okay, so I've got some r, right? I'm given the mass of the wheel. I'm given what else am I given? Maybe I'm told how far it goes.